This short introduction to radar teaches RYA Coastal Skipper and Yachtmaster theory students all they need to know to pass their exams. It's not intended to replace the full one-day RYA radar course, which must be taught in association with an approved simulator, and anyway, much practice and experience at sea operating a real radar is necessary in order to become competent enough to use radar for pilotage or collision avoidance. Radar is a valuable, practical and affordable asset on any vessel, which might navigate at night or in poor visibility, with setups like this one, which also incorporate a chart plotter, costing no more than £2,000 or $3,000. Unfortunately, whilst the technology contained in such equipment is extremely powerful, it's still essential to learn to operate it correctly, to interpret what you're seeing, and to understand its limitations before you can use it to make critical decisions that might affect the safety of your vessel. Let's look at the basic setup and operation. Rather obviously, we need to switch it on. Less obvious is that all but the very latest fully solid-state radar sets need time to warm up, typically around 1 minute. This is because the microwave pulses are generated by something called a magnetron, which is not dissimilar to an old-fashioned radio valve, and it needs time to reach its optimum temperature in order to generate a stable stream of pulses. Once it has warmed up, the radar set will normally enter standby mode, and you must switch it into transmit mode before it will start painting the screen. You might then adjust the brightness and contrast, particularly if you're navigating at night. You can use the gain control to adjust the radar's receiver's sensitivity. It's much like the squelch control on a VHF transceiver. If it's set too high, you get a lot of background noise on the picture which can obscure detail. If it's set too low, smaller targets will get lost. Happily, most modern radars set it optimally for you if you leave it in auto mode. Next, you might adjust the range. Presently, we're set to 10 miles. You can see this at the bottom of the display. Notice that the range rings are set at 2 miles, which means that the nearest ring is 2 miles from our position, the next is 4 miles, then 6 miles, 8 and 10 miles. Modern sets have a multifunction control which might operate in the following manner. Click the central button to select the function, and then rock the outer ring left or right to adjust the value. Here we press once to select range. Notice the associated box at the bottom of the screen is highlighted. Now we press on the left-hand side of the outer ring to reduce the range to 5 miles. The range rings are now set at 1, 2, 3, 4 and 5 miles. Rain makes an excellent radar reflector, easily obscuring important targets. In fact, if you're sailing in the tropics, you might well use radar to warn you of approaching squalls, especially at night. Fortunately, we can tune it out by adjusting the rain control. Just like reducing gain, we don't want to overdo it. Similarly, waves can confuse the picture, especially at short range, but they can also be tuned out. Now let's consider what's termed orientation. Here we're approaching a small group of islands in a motor cruiser. Notice the isolated danger mark approximately half a mile off our starboard bow. The most basic orientation mode is head up. We are in the center of the screen, and you might imagine that we're looking down from the top of a very high mast. The vertical line running up from the center of the screen corresponds to our heading and is called the ship's head marker. We've got the range set to 2.5 miles, and the nearest ring is half a mile from us. Notice the echo from the isolated danger mark just outside the first ring and slightly to starboard of the ship's head marker. You can see it moving slowly down the screen as we approach it. It's going to pass down our starboard side. You'll also notice that it's wobbling around a bit, and if you watch it together with the compass bar at the bottom of the display, you'll realize why. We're not managing to maintain a completely steady heading. It's very similar to what you might find if you were to try looking at the isolated danger mark through a pair of binoculars held in a fixed position. It would appear to be moving around. This is particularly a problem in smaller vessels and in a seaway, and can make accurate radar plotting, which we'll look at later, a bit of a challenge. The answer is to interface the radar set to an electronic compass, which enables what's known as a stabilized display. To take advantage of this, we switch the set into course-up orientation. Now you can see that even though we're not maintaining a steady heading, the radar set is working in conjunction with the electronic compass to determine an average course and is using that to stabilize the plot. Lastly, there's north-up. Here, the radar image is rotated such that the top of the screen represents north, and a separate ship's head marker is drawn on the screen to represent our course. Again, you can see that the display is stabilized, and that the isolated danger mark is going to pass down our starboard side. North-up is useful when comparing what we're seeing on our radar plot with a chart. Assuming you have a modern radar interfaced to an electronic compass, you should ignore head-up orientation and always use either course-up or north-up. Okay, let's go back to course-up at a range of 5 miles and take a look at what's known as the electronic bearing line, or EBL. When we first switch the electronic bearing line on, it will align itself with our course. Notice at the bottom of the screen it's set to 000 degrees, straight ahead. We can adjust it through 360 degrees. One great use of the electronic bearing line is to determine whether another vessel is on a steady bearing and therefore a collision risk. Here you can see that we set electronic bearing line on a small target approximately 70 degrees off our starboard bow, and as time progresses, the target remains on the electronic bearing line. Unless we, or the other vessel, alter course, a collision is likely. Have a think about what you might do in this situation. The variable range marker line allows us to measure the distance to a target. Once activated, the circle appears centered on the cursor and the display tells us its radius. Now, imagine that we're somewhere southeast of Anvil Point in poor visibility. Later you'll learn what makes a good radar target for measuring distance and bearing, But for now, just assume that the cliffs on Handfast Point at the north end of Swanage Bay show very distinctly on a radar plot. By using the electronic bearing line and variable range marker line, we can very accurately measure the distance and bearing to Old Harry Rocks, and that gives us a position fix. One very important thing to remember, though, is that the electronic bearing line is measured relative to our course 0 to 360 degrees in a clockwise direction. This can lead to confusion if you're not well practiced. In this case, our course is 025 degrees true, and the EBL is at 323 degrees. Therefore, Old Harry Rocks are on a true bearing of 348 degrees. Particularly when navigating in busy channels or estuaries, it can sometimes be difficult to discriminate between static targets, such as navigation buoys, and other vessels. Here we're in north-up mode, navigating roughly east down the Solent towards Spithead and Portsmouth. You can see the many large navigation buoys marking the channels in and out of Southampton. Because we are moving, they are all moving in concert relative to the cursor. Now look carefully to the southeast of the cursor. Can you see a moving target at a range of somewhere between 2 and 2.5 miles heading in our direction? If you were not being very diligent, it would be quite easy to miss. So, a very handy tool is the ability to add trails to moving targets, such that they stand out on the screen. Something else you can do is add a guard zone surrounding your vessel. Then, when any target enters the zone, an alarm can sound. In theory, this is great, but in practice it's only of any real value out in open water, because small craft radar won't be able to discriminate between static and moving targets. So, for example, passing a major navigation buoy would set off the alarm. Another great way to distinguish between static and moving targets is to overlay your radar plot onto your chart. Now you can see that radar targets sit neatly on top of their charted feature, and if you see a target which is not on the chart, it's most likely another vessel, unless of course you haven't updated your chart recently. Overlaying the plot on the chart is also a good way to check that your scanner is correctly aligned in your vessel. As I hope you already know, it's also not a great idea to drive your vessel around the chart plotter, but sometimes in fog being able to see both chart and radar plot in north-up orientation can provide a safe means of navigating even within narrow channels. OK, you've learned a little about operating radar. Now we'll look at what we can see with it. As I guess you already understand, radar works by pinging pulses of electromagnetic radiation and listening for them to be returned by radar targets. By measuring the time it takes for a pulse to return, the radar can calculate the distance to the target. So here we are looking at a ship about half a mile away, just off our starboard bow. As our scanner rotates, a beam of pulses passes across the ship, and it lights up as a target on our radar screen. On old-fashioned radars, which used cathode ray tubes, the target would light up and then fade until the radar beam passed over the target again. Modern radars, containing image processing software and displaying targets on an LCD screen, don't do this. Here we are approaching a small group of islands. One of the first things to realize is that radar is line of sight. It cannot see around corners. So, if there were a ship out of sight behind the islands, it won't show up on your radar screen. In terms of what will and will not show up, as with many things in life, size is everything. The bigger the target, the better it will show up on radar. Big ships and large fishing vessels make excellent targets, as do most radar reflectors, especially active radar transponders like the Echo Max in the bottom right-hand corner of the screen, which, when it receives an incoming stream of radar pulses, amplifies them before sending them back, making your vessel look bigger than it really is. On the flip side, sailing vessels, whether constructed from wood or GRP, small fishing vessels, and spherical or cylindrical buoys make very poor targets, especially when hidden amongst waves. Similarly, modern warships are designed so that they don't present surfaces perpendicular to incoming radar, scattering the pulses in an attempt to make themselves less visible. Cliffs make excellent radar targets, whereas gently sloping coastlines, mudflats, or marshes and sand dunes might be invisible. Some navigation aids, like West Bramble West Cardinal Buoy in the central Solent, carry what are known as Raycon beacons, commonly known as Raycons. When a Raycon receives a radar pulse, it responds with a signal on the same frequency, which puts an image on the radar display. This takes the form of a short line of dots and dashes forming a Morse character, radiating away from the location of the beacon. This one signals the Morse code for the letter T, Tango, which is 1 dash. Radar cannot see over the horizon, which means that you need to mount your scanner as high as possible to maximize its range. Just a word of warning though, whilst the weight of scanners is coming down, mounting a scanner high up on a small sailing vessel's mast can have an extremely detrimental impact on the vessel's stability. The radar horizon is pretty much the same as the visible horizon, and can be calculated as a function of the height of the scanner using the formula distance to horizon in miles equals 2.2 times the square root of the height of the scanner in meters. For a 40-foot motor yacht, this might mean a radar horizon of about 5 miles. Of course, it's not quite that bad because the target is above the surface of the sea. So, for example, the aforementioned motor yacht could expect to detect a large container ship at a range of about 13 miles. Or a major navigation buoy, such as this safe water buoy, at a range of about 8 miles. A small fishing vessel at 2 miles, or a small fiberglass sailing vessel at 1 mile. Of course, if the motor yacht is doing 30 knots, then it will cover that 1 mile in 2 minutes. On the other hand, if the small yacht is equipped with a top-quality radar reflector mounted well up her mast, then she should be seen from a range of around 5 miles. As you might imagine from this photograph, small vessels and even larger fishing vessels can often be hidden in rough conditions, and your instructor once very nearly collided with a fishing vessel during a gale in the English Channel for just this reason. It was only as she passed astern of us, not more than 50 feet away, that we saw her. It's also important to realize that your radar's vertical beam width is quite narrow, and it's not unusual for it to be pointing at the sky, or the sea. If the scanner is mounted on a planing power vessel, it's important that when the vessel is stationary, it's angled slightly down towards the bow, to take account of the bow rising as the vessel comes onto the plane. Your instructor was once contacted by the owner of a brand spanking new £1 million motor yacht, not dissimilar to this one, asking for some radar instruction. As we were motoring slowly down the Beaulieu River, the proud new owner said, "I don't understand this radar. I can never see anything closer than about half a mile ahead, and the other day we nearly ploughed into a major navigation buoy as a result." Sure enough, the moment we left the river entrance, he opened the throttle up to maximum, we leapt up onto the plane, accelerated to 30 knots with a radar scanner pointing at the sky. Not only could we not see small targets ahead of us, but also a major container ship navigating round the brambles towards Southampton Water disappeared from the screen. It's just as bad on sailing vessels when you are heeled over. Small targets close to you might be invisible. It is possible to buy gimbaled radar mounts, but they are heavy, so few vessels fit them. The next thing to understand is that your radar beam is not like a laser beam. The pattern is much more like this, with the bulges known as side lobes. This means that large targets close to your vessel will not appear as a distinct image, but will look much more like an arc, which in extreme circumstances can encircle the screen. Radar beam width is a function of the size of your scanner. The bigger the scanner, the narrower the beam, which is why land-based scanners are sometimes very large. Small scanners, such as might be found on leisure vessels, might have beam width of 7 degrees, whereas large scanners on ships might have beam width of anything down to 1 degree. This means the small yacht's radar will not be able to discriminate between two targets that are less than 7 degrees apart. 7 degrees at 3 miles is approximately 600 meters. This vessel is attempting to navigate into the northern entrance to Quarantine Bay. She is approximately 2 miles from the entrance, which, even at its widest point, is a quarter of a mile wide. If her beam width is 7 degrees, the entrance will not show up on her radar. And because even the most basic radar with a high beam width can still measure distance with great precision, if circumstances permit, it's preferable to plot a fix using the range to 2 or more distinct targets. Admittedly, the very latest radars, which employ new scanner technology and advanced signal processing, can do better, but, of course, it will be some while before these are retrofitted to vessels already equipped with perfectly good last-generation radar. Now let's look at the role of radar in collision avoidance. Firstly, we need to look at what the collision regulations have to say about the matter. Section 1, Rule 7, states that we must use all available means to determine the risk of collision, including radar if available. So, if your vessel is equipped with radar, you must use it. Section 2, Rules 11 to 18, define the conduct of vessels in sight of one another. For example, in Rule 15 it says that when two power-driven vessels are crossing, the vessel which has the other on her own starboard side shall keep out of the way. Rule 19 chucks all this out of the window. It applies to vessels not in sight of one another. In other words, in fog or restricted visibility. There is no give way and stand on vessel. Any vessel which detects the risk of collision with another vessel by radar alone must take early and substantial action to avoid the other. You will already know that in good visibility you can determine the risk of collision by taking a compass bearing on the other vessel. Assuming that both vessels maintain their course and speed, if the bearing remains constant, then the vessels will collide. If the bearing alters over time, they will probably miss each other. Here we've drawn an electronic bearing line and range rings centered on our vessel, and you can see that the other vessel travels down the EBL whilst the range decreases. We will collide. We can ignore our own vessel's movement to get some idea how this might look on our radar screen. If the bearing changes, then we probably won't collide, although you might come close. Our closest point of approach is just what it says it is, the point at which two vessels come closest to each other. In this illustration, if the range rings were set at half a mile, our CPA would be approximately 0.7 miles. Determining the safe CPA obviously depends on the types of vessels, their speed, and the conditions. Two large ships in open water might elect to come no closer than a mile, whereas two relatively slow-moving, small craft in confined waters might decide that a cable, approximately 200 meters, is enough. We can calculate the CPA using what is known as a plotting sheet. Our first plot at 10:12 shows a target approximately 45 degrees off the starboard bow at a range of just over 5 miles. 6 minutes later, the bearing has decreased slightly and the range reduced to 4 miles. At 10:24, the bearing is 034 degrees and the range 3 miles. If we join the three plots, we can see the target's course relative to ours, and that the CPA is approximately 1.5 miles. To calculate time to CPA, we need to determine the target's speed relative to ours. We can do this by measuring how far the target moved on screen in 12 minutes. In this case, approximately 2.5 miles, giving a relative speed of 12.5 knots. From the 10:24 position to the CPA is approximately 2.7 miles, which at 12.5 knots will take 13 minutes. So, what if the CPA indicates that we are going to come dangerously close? Let's lift the fog for a moment. Assuming that we are a sailing vessel in open water and that the other vessel is a motor yacht. Does the fact that we are under sail and the other vessel is under power have any bearing on the situation? No, it does not, because Rule 19 applies, and we must alter course to avoid the collision. If you think about it, this makes total sense, because, using radar alone, we cannot tell whether the other vessel is a power-driven vessel, another sailing vessel, a fishing vessel, or whatever, and neither can they. We should tack, altering course 90 degrees starboard. Very expensive commercial radar sets, such as might be found in large ships, are equipped with ARPA, which stands for Automatic Radar Plotting Aid. It can automatically identify and plot multiple targets. Less expensive radar sets, such as likely to be found on leisure vessels, can be equipped with MARPA, Mini Automated Radar Plotting Aid. The key difference being that with MARPA, the operator has to identify targets before automatic plotting can start. Once MARPA is enabled, the operator can move the cursor over the target to start tracking it. Initially, MARPA paints a square box around the target, telling you that it hasn't yet managed to get a good enough fix to calculate CPA, etc. After some while, with the exact time depending on how well the target is being resolved, the square box will switch to a circle, with a vector extending in the direction of the target's relative course. Normally, the vector shows how far the target will move relative to your position in 6 minutes. In this case, CPA will occur in approximately 15 minutes at 0.74 miles, and the target speed over the ground is 20 knots. You can set an alarm threshold on CPA. Of course, if you are also equipped with AIS, and the target has an active AIS transponder, then you can get more information about it, which will be helpful if you need to call it up on the VHF. See the Collision Regulations and Electronic Navigation lesson for more information. Okay, that's an introduction to radar. Now you need to get some hands-on experience. There are a few PC-based radar simulators out there, but those priced within reach of the average leisure sailor, notably Bridge Command and Lightmaster Radar Simulator, aren't very good, and you can waste an awful lot of time trying to set them up and making sense of their quirky user interfaces. Much better would be to hire a qualified RYA radar instructor and vessel for a day or two to get some real-world practice in good visibility, when you can compare what you're seeing on the radar with what you see by eye, in order to make a safe assessment of the situation before acting on the radar plot alone.